Howdy, folks, and welcome to my channel, or welcome back to the channel. Um, Hold on a moment. I don't think I'm using the right camera. I am not. Let's see if this is better. Extreme close-up. Actually, I don't care for that. Let's use the MacBook. All right, cool. Hey, I got a new sub, Ben Dover. Hi, Ben. Howdy, Ben. Roke. Howdy. Georg. Georg was kind enough to point out actually a mistake that I made on my inclined plane video, and I've been trying to carve out enough time to actually make an errata video where I address that, but that's on for another time. So today I'm going to be giving a lecture, a continuation of the geology lecture that I was talking about in the previous two lectures. I thought I was moving towards planetary atmospheres, but as it turns out on my schedule, what I'm going to be doing is I'm going to be looking at the geologies of these planets or these worlds in a little bit more depth. And so today we're going to be focusing on Mercury, the Moon, and Venus. If I have time, then I'll move into go into Mars. I do have a deadline, or basically a stopping point, or a deadline of about an hour for this stream, because I am finally going to do what I've been advertising for the last week or so, which is at 4:30 Eastern Standard, or Eastern Daylight, basically an hour and a half from now, I'm going to be going live again, and I am going to be talking about the JWST observations of galaxies in the early universe. There's been a lot of SciComm out there. There's a lot of discussion among flat Earth folks, and also among folks who come to my public nights, who seem to think that these JWST observations somehow debunk the Big Bang. What I'm going to do is I'm going to explain, as best to my ability, what these observations are, what they truly are, basically what they're looking at, the limitations of the observations, what the implications of those are, all in the context of all in the context within our current understanding of how galaxies evolve in the early universe. So I'll probably start off with the explanation and then go into the observations. So yeah, so that will be actually open to anyone who wants to have a conversation. So I will actually have, if anyone is around and wants to, I will give them the link to my StreamYard and have you on, and we can just talk about talk about any of that, or really anything. And so that'll be happening in 4:30. So yeah, I have a bit of a time limit. So let's get started. All right. Apologize for the casual dress. It's gotten very, very warm very, very quickly, and so all of my short sleeve, professional looking button downs are needing to be washed and definitively needing to be ironed. So what am I doing here? I'm doing that. All right. Actually, I'm going to do that. All right, folks. Like I said, we're going to be talking about Mercury, Venus, and Mars in a little bit more depth than I did before. And I may, in fact, be sort of repeating myself, but I definitely have images to really back up some of the things I was talking about last time. These three are terrestrial worlds. I am defining world, just so you know, I am defining a world as something that is spherical under its own mass. So it doesn't matter, it can be revolving around the sun, or it can be revolving around a planet. So in this case, the moon is a world. Now, why, or what are we trying to what am I trying to accomplish in this lecture? Our goals today are to learn about the geologic processes that shape the moon, and learn about the geologic processes that shape Mercury. Because on first blush, when you see pictures of the moon and see pictures of Mercury, it's very difficult to tell them apart. And in actuality, I can show you pictures close-up pictures of parts of the moon and close-up pictures of parts of Mercury And I'll bet dollars to donuts, you will not be able to tell them apart. They are very similar in terms of color. They're very similar in terms of uh, surface features. And that is because their compositions, or at least their surface compositions, are very similar to one another, at least in certain areas. And they've undergone similar types of geologic processes. No, it's a dress. It's a shirt, Nimrod. Ah, sheesh. Um, so, what about the moon? What are the geologic processes that shape the moon? Well, I've mentioned this before, and the only naked eye geologic feature on the moon that you can see are those dark stains, what we call lunar mare, derived from the Latin seas. So, in singular, it's a mare, M-A-R-E. In plural, is it? I think I might have that backwards. Maria. Yeah, I get. I could actually have this backwards. I tend to use it interchangeably, but I believe the singular is M-A-R-E for sea, and then the plural is Maria, M-A-R-I-A. Regardless, what we're talking about are these dark areas on the moon that obviously you can see naked eye, and these are very large in extent. They typically are on, if you approximate them as circles, they typically have radii of upwards to like in the upper hundreds of kilometers or even lower thousands of kilometers in size. But when you take a closer look at them, they become a little bit more interesting in that when you take a closer look at the moon, what we find is the moon's surface outside of these mare or maria are heavily cratered, while as inside, as you can see here, the inside feature really is devoid of cratering. It's very, very smooth, or at least comparatively, it's much smoother than comparatively the highlands, which we call them on the outside. And they are, as not really can see it in the inset, but in the other image, you can definitely see that mare are darker than the highlands. The reason for this is because of how it formed. When we look at the lunar mare, the moon surface, based on our understanding and our observations, we believe that the surface prior to the mare's existence looked very much like what we see on the left. It's very much like what we see with what we call the lunar highlands, just a heavily cratered, lighter gray colored surface. And then you have basically a very large impactor hits the world, hits the surface, and cracks it open. And here, as I discussed last time, because of the way the moon formed, and it occurs to me that I may not have ever actually gone into the specifics of how the moon has formed. I'll need to check that. If not, then I'll do a special lecture on that just specifically. But regardless, when the moon formed, what happened was because of gravity, the core is slightly offset. It's actually closer to the Earth than the geometric center of the moon is. And because of that, the lithosphere on our side, or the near side, is thinner. So when an impact happens, it can be some of these were so large that it actually broke the lithosphere, cracked the lithosphere, and beneath it was very low viscosity lava that was more similar to the flow or how water flows than how oil flows. And so that upwelled, that came up and basically flooded the surrounding area until the whole thing cooled off. And so that really, how big it is, really would depend on how hot that particular pocket of magma was. If it wasn't very hot or wasn't comparatively hot, then you get a smaller mare because it takes it less time to freeze. If it's hotter mare, then it's further out and you get something bigger. And then it basically, like I said, freezes over and you get a nice kind of basalt driveway. You get a nice flat kind of plain made out of basaltic or volcanic rock. hence why it is darker or has a lower albedo than, or reflectivity than, the anorthosite rock, which is of the highland, which makes up the highlands. But, and we also, as before, I talked about the era of heavy bombardment. We know, or again from evidence, and this is one of the key pieces of it, that a lot of the impacts we see on Mercury, we see on the moon, we see elsewhere, most of those craters were created in a very short period right after the formation of the planets or the worlds. So we're talking about somewhere around 4 billion years ago at the start of it, and it lasted for roughly 500 million years or 500 million years. And we know this, and we know that it has a somewhat of a dramatic cutoff because of the population density of the craters. On the left, like I said, that picture is a representation of the lunar highlands, basically a good portion of the lunar surface, and you can see that there are craters on top of craters, and really it's covered in craters. So lots and lots of craters. Whereas with the Moray, these heavy impactors came in, blocked out or eradicated the evidence of the previous cratering. And then what we see, or rather we don't see, is continued cratering. We don't see a lot of large impacts within the Mare itself. So we know that after this paving has occurred, few things have come down and actually disturbed it or messed up the driveway. We also see tectonic features on the moon. This is I believe, one of the Apollo shots. You see those ridges. That indicates that during a portion of the geologic history where the lunar surface was molten in one form or another, either because of an impact or more likely because of when it was still forming, you had convective action in the mantle, which caused a squeezing of the lunar surface, or an expansion of the lunar surface at that locality, at that local area. And you can see that kind of linear feature. That's where, so there are a few things, there are a few legitimate mountain ranges on the moon, although those are not to be confused with what we refer to as mountain ranges that are actually lips of a crater, of a very, very old crater. But you can get these nice raised features because of tectonic action. I referred to, last time again, I referred to the moon, and I will also say this of Mercury. We refer to these worlds as geologically dead. The reason for that is because we believe that these worlds are essentially solid from crust to core. That does not mean that they are a constant temperature, or they are one temperature from crust to core, but there is nowhere in the world where the internal temperature is high enough to be in any kind of molten state. And without a molten state, without some kind of liquid or semi-liquid fluid, I guess, or phase, this matter being in that phase, without that, you cannot have things like volcanism. You cannot have things like tectonics. You certainly can't have plate tectonics. And so a lot of these geologic activities just cannot happen unless you have a semi-fluid mantle region for that to happen. Because of that, if you have no geologic activity, you have no volcanism, as I've said, which means you also have no outgassing. So, depending on the size of your planet, you can easily lose, or you could have lost your atmosphere, both your primary and secondary atmospheres, within the last 4 billion years. And without outgassing, you can't replace them. So again, the moon and Mercury, as I'll talk about later on, essentially have no atmospheres. They have something equivalent to what we have on Earth in terms of an exosphere. And what that means really is a shell of a shell of negatively charged particles or electrons or ions surrounding it. You wouldn't really conventionally call that an atmosphere. But again, depending on who you ask, the exosphere is part of our atmosphere. So in that case, Mercury and the moon do have an atmosphere, but it's very exceedingly tenuous. I don't think anyone would really consider it an atmosphere. In terms of the lunar surface, this is obviously a famous picture of one of the Apollo boots. I don't know if it's Neil or Buzz's, but this is one of the first boot prints that are on the surface. And when I say are, it's probably still there. There isn't a lot of erosion that happens on the moon, particularly in terms of winds features. So that print is probably still there. It may look a little bit more blurred, but it's probably still there. The reason why it looks like that is because the moon is covered, and presumably also Mercury. We obviously haven't landed on it, so we can't really tell. We don't have any direct evidence of it, but presumably both worlds are covered in about a thick 6-inch thick band of what we call regolith. On the moon, it's definitely called a regolith. It's really just dust or a fine powder. That was actually one of the open questions about the lunar lander. And that was one of the things that they were worried about when it came to the lunar landing, was there were speculations as to there was going to be regolith. The regolith was expected, but the depth was unknown. They didn't know exactly how much erosion that caused this this fine powder to occur. And the reason why that fine powder is there is because, as I mentioned before, we have, if you're talking about impactors or crater or basically impactors, we are ongoing, like cratering or impact craters or impactors are an ongoing thing, because there is millions upon millions upon millions of micrometeorites, basically dust grains about the size of a micron. And that is just streaming through the solar system. Most of it is contained within the ecliptic. We refer to that as the zodiacal dust. And these rocks are traveling at a very, very high rate of speed. For our atmosphere, they get essentially pulverized or dissolved. For the moon, not so much. They come and they smack into the rock, and on a subatomic level, they will break bonds. They will cause electrons to go flying. They will break molecular bonds. And given enough time, very much like sandpaper, fine grit sandpaper, it's going to turn that surface into powder. So the NASA, that is actually pretty awesome. NASA was concerned about the depth, and oddly enough, the reason why, just a little bit of a diversion. If you remember the footage, Neil had to, or it's either Neil or Buzz, I can't remember which. I think it was Neil. When he came down, he actually kind of had to drop down significantly, and the reason for that is because the regolith was not nearly as thick as they were expecting it to be. The lander landed much softer, in a sense, than they expected. They actually had designed it so that there would be shock absorbers, shock absorbers, but also they were taking into account that maybe the lithosphere was more dust than it actually was, or not lithosphere, the surface was more dust than it actually was, and it would sink a little bit deeper, so the bottom rung would actually be fairly close to the ground. Well, as it happened, that wasn't the case. The bottom rung was actually significantly off the ground, which is why you see Neil Armstrong kind of jump off the ladder and get onto the ground, is because the NASA actually thought it was going to sink lower in the dirt. And apparently this stuff gets everywhere. Apparently this stuff is very much like you would expect, is like sand. And I would put money on the fact that this powder is electrically charged. It is. And so electrostatic, this moon dust got everywhere. Like they could not get rid of it. It was one of the biggest pains that the astronauts had to deal with, because they tracked this stuff back into the LEM and they just couldn't get rid of it. So imagine basically going to the beach and getting stuck in your car with a whole bunch of sand in it, and staying in your car for I don't know, days in order to get back. Hi, Mark. Howdy, Mark. All right. So, what geologic processes shaped Mercury? As you can imagine, in some cases, because Mercury and Mars are similar in appearance, you can expect that there are similar geologic processes that occurred. But there is one. Well, there are two major differences. One, the moon formed around the Earth, and so that consequently that caused the core of the moon to be offset from the geometric center of the moon, which in turn allowed for the creation of Mare. For Mercury, that's not the case. So the lithosphere of Mercury is, roughly speaking, that which ever existed, is roughly uniform all the way around. And so when you have impactors, there are no mare on the surface of Mercury that we can observe, that we've observed, because of the fact that the lithosphere was all the way around, was thick enough to not break and split apart and have an upflow of lava on that surface. But Mercury has went through a different type of or it went through a category. It had a, how should I put this? Sort of a very violent history, which apparently my slides tell me I haven't gotten to yet. But again, as you can see, we have Mercury is a combination of cratering and smooth surfaces, most likely ancient lava flows. Not lava flows that create mare, but lava flows that more than likely, or that came from volcanoes or possible tectonic activity, localized splitting of the crust, not due to impacts, but due to just geologic activity, normal geologic activity. We do see signs of dormant volcanoes on this on the world. Aw, so glad you think I'm doing great. We can also see that essentially direct evidence that uh, outgassing happened. And what we can see is, if we look at the lunar or the Mercurian surface in visible light, and what we can see see basically the surface of this cratered region. If we look at it, looking at it with a particular filter, looking for a particular, essentially particular mineral, what we can find, what we see is underneath this crater there are hollow points. There are hollow areas where gases existed and were potentially released out into space or out into the atmosphere when when Mercury was still geologically active. Now, I said that Mercury had a violent past, and so it's actually interesting in the sense that all four terrestrial worlds seem to have been hit, have evidence that shows that they seem to have been hit by a large impactor at some point in their history, except Mars. Mars may not have been big enough, I don't know. But Mercury, Venus, and Earth all show signs that are best explained that they were smacked into something. They were smacked into something very large earlier on in their history. Wow. Thanks. So, um, uh, sorry. My professor thing came up earlier, so that kind of mine went there. For the Earth, that's one of the reasons why we believe that how the moon formed, why the moon is the way it is because it's essentially ejecta from a very large impact of a Martian-sized impactor onto the Earth's surface, which blew off material, which then later coalesced into the moon. Venus has a rotation axis that is flipped. That is its rotation axis is 91 degrees. So it doesn't rotate counterclockwise when viewed from the north, it rotates clockwise. Again, we believe that some kind of impact literally flipped it. flip the rotation axis of that planet. For Mercury, what we believe is the reason why we know that it has an overly large core, overly large iron and nickel core, roughly basically the same size as the Venus and the Earth, a little bit smaller, but on par with Venus and the Earth. But Mercury is significantly smaller in overall size. Here, what happened is something very similar to the Earth, where something of similar size but smaller hit an oblique angle from Mercury, blew off material, but unlike with the Earth, where the material didn't have a sufficient enough escape speed to leave the Earth's gravitational influence, for Mercury it did. It basically got blown off into space, leaving behind a differentiated iron nickel core and a thinner piece of mantle around it. And what that caused right after that was a massive contraction of Mercury. We see evidence of that are from what we call scarps. If you look here, if you look at the picture on the right, what you can see are basically linear-ish features that have shadows, and you can, by measuring the length of those shadows, you can measure the height of those cliffs. Those cliffs can exceed meet 2-3 kilometers in height. These are sheer cliff faces that are kilometers in height. The way they got that is essentially the lunar surface, or the Mercurian surface, has a certain surface area, and it shrank. Well, if you shrink something, the surface area has to get smaller, but the amount of material is still the same. The amount of material isn't going anywhere. Unlike with plate tectonics, where one plate subducts into the next one, this surface is solid, essentially. There are no plates. And so the surface cracks, and some of the surface kind of stays up, and some of the surface actually goes kind of down into it. So we see evidence of tectonic activity on Mercury. So what about Venus? What geologic processes shape Venus, and what about plate tectonics? So what we know about the Venusian surface, we get from radar. Obviously, we cannot see the Venusian surface. The atmosphere of Venus is so thick and so dense that the opacity is basically 100%. It is not transparent to visible light whatsoever. You cannot visibly look down to the surface of Venus. So how do we know anything about the Venusian surface? Satellites. Specifically, I'm going to be giving you images taken by the Magellan probe. I don't know if there's been a more recent probe, but definitely these images were taken by Magellan. And the way they did this was essentially radar mapping. The Magellan spacecraft orbited around and shot a radar pulse down onto the surface. It reflected back up, and based on the amount of time it took for that return pulse to come back, you now have a distance. And so you now have basically a kind of a reverse elevation. So the longer it took for the signal to get back to you, the lower down in elevation that particular part of the surface was. So they did very high angular resolution radar mapping of the Venusian surface. Something like this. Well, this would actually be a first attempt, very low resolution image on top of a high resolution image. But we can see a lot of different things. We can see craters. Here is an example of what I had previously referred to as a complex crater, or a crater with a central peak. So you have the crater rim, and then inside you have the central peak that rises up, and you can also see the ejecta from around that crater that got blown out from the explosion. But it has fewer of these impact craters than the moon, Mercury, or Mars. Hopefully you can guess as to why. The reason why it has fewer impact craters is because the atmosphere is so thick, and has been very thick for its entire lifespan, that only the most energetic, or only the largest only the largest and most energetic or fastest moving impactors were able to manage to get through the atmosphere and reach the surface. So a good portion, a good fraction of the atmosphere, or a good fraction of the comets or asteroids that were incoming, got destroyed before they could hit the surface. On top of that, what we see is volcanoes. We see both stratovolcanoes or cone volcanoes, Mount Doom type volcanoes, and shield volcanoes, like the ones we see on like Olympus Mons, for example. We also, as I've mentioned before, we see tectonics. Well, I'll get back to volcanism in a second. We see tectonic features. We again see this sort of spreading of the lunar or the Venusian surface due to underlying convective activity, which stretches the surface on short time scales and creates these sort of valleys that we see. In terms of erosion, this is one of the few images that have been taken from the surface of Venus. The surface pressure of Venus is 90 times that of the surface pressure that you are experiencing right now. So imagine feeling essentially a weight, feeling 90 G, I guess, or multiply your weight by 90. And that's what you would feel, you would experience on the surface of Venus, because of the massive amount of mass of the atmosphere sitting on top of you. So the only people to do this, the only people to succeed, as far as I remember, of putting a spacecraft on Venus and having it survive for any length of time, were the Soviets. And this was the Venera 2 probe. I think Venera 3 also managed to get on the surface and stay there. But it only lasted for an hour before it cooked. I don't know if it cooked or if it got crushed, because also the surface of Venus is ridiculously hot. It's hundreds of it's about 400. Surface, I think, is roughly a little bit over 400 degrees Celsius. So it's very hot. So a lot of the electronics would certainly burn out after a while. But that surface pressure is really what crushes things to death. Like I said, it only lasted an hour, but it did take these and be able to transmit these images back to us. And what you're seeing here is you're seeing a roughly flat plane or a flat location. But what I want you to really look at is the edges. So you can see that the surface is cracked, and you can see a couple of different localized sort of rocks. When you look at those rocks and you look at those cracks, look at the edges. And those edges are sharp. There isn't a lot of rounding to them. And what that tells you is that there's not a lot of erosion going on. There's very little wind on the surface of Venus, so there's very little action that picks up dust from one place and then smacks it onto another surface and erodes that surface down to make it more roundish. So we can see from that picture that from those cracks that erosion isn't really a thing on Venus. The other thing you can see is because of the flatness. Now there are various other reasons why this region could be flat, but usually with like Mars or Moon, where you see a sort of a flat plane, you also do see rocks that significantly stick up from the surface. Here, not so much. The rocks are really, really flat. So again, this is indicative of the fact that the surface pressure on Venus is immensely large. It's 90 times the atmospheric pressure on the Earth. Thought Venus was the same Earth as mass. That's correct. So Venus, when I was a child and coming up, Venus was also often referred to as the Earth's sister world, in that because it has the same mass, it has the same radius, it has roughly the same density and roughly the same surface gravity. The difference between Venus and Earth is the fact that our atmosphere is of a certain weight. Basically, the air above us weighs a certain amount. On Venus, on the other hand, the atmosphere, the extended envelope of gas above them, is much more significant. I would hesitate to say that it's 90 times more massive than our atmosphere, but it definitely produces a surface pressure that is 90 times greater. So it's not that gravity is causing. I really did misspeak when I talked about experiencing G forces. I apologize for that. The G force on the person is the same on Venus and Earth, roughly speaking. The difference is that above you, the air has a lot more mass and therefore a lot more weight, and that weight is pushing down on top of you. This is an issue of we sort of neglect surface pressure as a force, or the weight of the atmosphere as a force when we're talking about everyday terrestrial life. That's not something that you could really do on Venus. That is something that you have to see. Does Venus have plate tectonics? Now, I think in a couple times I've actually misquoted myself. I think I've said that the surface was repaved like 150 million years ago. Actually, apparently it's 750 million years ago. So we don't believe that there are plates. We don't see evidence of subduction. We don't see large trenches that would indicate the movement of plates away from each other. But also we see based on given the factors of the atmosphere and based on just crater numbering, we come to the conclusion that the entirety of the surface of the world has been repaved within the last 750 million years. Given the number of impacts that should have hit Venus and the number of impactors that should have survived going through its atmosphere, we would expect that the Venusian surface would expect that the Venusian surface would have a higher number of craters than it does currently. Because, as you remember, there's no water and there's no wind. Therefore, there's no erosion. And there's no plate tectonics, so the surface isn't getting subducted, destroyed, and recreated. So with the cratering is far too few to be explained to not. There are far too little craters to be explained, other than at some point the entirety of the Venusian surface got resurfaced due to volcanic activity. Now, why this is the case, we don't really know. The two sort of culprits that you can immediately think to are because plates get formed by convective action cracking a lithosphere. You can either blame one or two or both things. Either for some reason on Venus, the convective action beneath the lithosphere is weaker for some reason, or the lithosphere is thicker. So it could possibly be that Venus is a bit smaller than the Earth, so it's possible that it has cooled off faster than the Earth, and so therefore the lithosphere is thicker than what we see on the Earth. And so if it may have at one point had plates, but those plates have fused together into a solid sphere. Again, it's really open science at this point in terms of, because Venus, as you might imagine, is exceedingly hard to study. You can only surface map it using radar. You can't look at it visually. You have that basically cloud deck in the way. So, and obviously we haven't been able to land on it really at all. So putting seismographs onto the surface is also problematic. The seismographs would help us understand Venusian earthquakes. If there are a lot of earthquakes, that would seem to indicate that there is a lot of mantle activity going on underneath the surface, so you would expect that the lithosphere would be larger. You can also map out what the interior would look like, but since nothing can really survive on the Venusian surface for longer than an hour, that's been really, really hard to do. Oh, sorry to hear that, Nimrod. So 40 minutes. I got 20 minutes. Let's talk about. Let's start talking about geology of Mars for a moment. Actually, I don't want to cut through. Don't want to start Mars and then cut way through it. So I'll just leave it this. So that was my lecture for today. Venus, Mercury, and Mars. I hope you all have found it more entertaining than, who was it? Glock Flob. I hope you found this educational. I hope you find it entertaining. So if you like this sort of content, please like, share, and subscribe. If you have any questions, please let me know, either in the comments or in here or in the comment section, and I will try to get them answered as quickly as possible. You can also, on my, I haven't been saying this, but you can also find my email address and my Discord server on my YouTube page somewhere. So feel free to email me any questions that you have, and feel free to join my Discord and ask me any questions there. I am on Discord probably far too many times, or far too much. So that is probably, if you really want to get to me, get an answer from me very quickly, or the quickest, Discord is probably the best way to get in contact with me. If you'd like to support what we do here at George Mason financially, please feel free to become a patron, and there are benefits, or hit me up on PayPal. All proceeds go to the university or go to the student club to make things snazzier. Buy scopes, lights, that sort of thing. Okay, so Rob, didn't Venus kill several Russian probes? Yes, Nimrod. So I like to call them Soviets as opposed to Russians, but yes. So I had a lot of, shall we call them boomers? Let's call them boomers. A lot of my professors were, particularly on the planetary side, were of the older generation. Their formative years were during the Cold War. And so a number of them took almost a certain amount of glee in describing in contrasting the Soviet space efforts to the American space efforts, particularly in Mars's case, in that the number of missions that the Soviets sent to Mars that simply missed the planet is kind of amusing. But the one thing that the Soviets did that outshined the United States was they were able, the Venera 2 and the Venera 3, I think, were able to land on Venus and survive long enough to take photos, take scientific data, and transmit it back. The United States, as far as I know, when it comes to going into the Venusian atmosphere, the best we could get was maybe halfway, or we couldn't get to the surface. The probes all were destroyed well before they got to the surface. So in that sense, the Soviets beat us. Since then, it has not been a priority for us to design a mission to land on the surface of Venus. Right now, orbiters and flybys seem to be sufficient, at least in terms of priority. If that'll change, who knows? We only get $50 some odd million a day. You can only spend that so much. So NASA. So yeah. Yes, the Soviets did get a lot of amazing data, which I'm glad exists. Or half of my discussion of Venus would be, well, not half, but a good chunk of my discussion of Venus would be more speculative than it is now. But Shouldn't then be able to increase the pressure inside the probes as needed to keep them alive? I'm not sure. I'm not a structural engineer. You would think with submarines, that's how they, I imagine that's how submarines work, is you pressurize the interior cabin to help um, to help prevent the sub from crushing at depth. But on top of that, I think you have to have a substructure, or a structure of the submarine, rather, on the inside, that also helps fortify it against that pressure. And and what I would imagine is that requires a lot of metal. It requires a lot of material, and that material obviously has mass. And when you send things, the biggest thing that any scientific uh, or satellite or what have you, and the biggest consideration that they have is mass. Is that all of your science has to be done within a certain mass limit, because the rocket can only transport so much. So, oh yeah, it's heat. If you drop through the Venusian atmosphere, what happens is, as soon as you hit the top of the cloud deck, you now have to deal with hundreds of kilometers per hour fast winds. Then very quickly, because the atmosphere is ionized, you have to deal with lightning strikes. So there is a lot of lightning going on just beneath the cloud deck of Venus. I believe there have been. You can Google it. You can actually see lightning. There has been lightning captured on Venus's surface, or a visible surface. In addition to that, so you've got hundreds of kilometers per hour winds. You've got lightning to dodge. Then you go through a layer of um, liquid sulfuric acid. So you have sulfuric acid to navigate through, which will rain down through the atmosphere. And then, because of the heat that and as you're going down, the temperature is only getting hotter and hotter. The pressure is only getting hotter, or larger and larger. That sulfuric acid rain will actually no longer be liquid because of the high temperatures, and it will vaporize. So you have sulfuric acid vapor that you're going through because of the high pressures and high temperatures. And I'm not certain of this, but I'm guessing that once you get down to low enough, the heat is going to be sufficiently large that sulfuric acid cannot exist in a molecular state. But there, I'm just completely guessing. So yeah, Nimrod, you ain't stupid. All right, Georg. Yes, and Georg, you're right. The atmospheric the heat is immense. Is hundreds of Celsius. I don't know. I don't know if heat is a bigger problem than pressure, because those Venera, like, I'll look into that, because my understanding was that the Venera probes ended because they got crushed, not because they melted. But I could be wrong. Both are a serious problem. Anyway, for those of you who came in late, in about an hour, in about 45 minutes, I'm going to go live again, and I'm going to start off by talking about the JWST observations of the early universe. I'm going to explain what our current understanding of how the early universe began, or how the early galaxies began, specifically looking at the masses of what those galaxies should be, and then comparing that to, I'm going to be using one paper in specific, but I believe all of the previous papers have been of a similar observational design. I'm going to talk about what that paper says. I'm going to talk about the methodology of that paper, and what the limitations of that methodology have in relation to the claims they make. So the claim is, by some, that these observations have somehow debunked the Big Bang. I can assure you right now, they have not. And so what I will tell you is they have, if they are born to be true, these massive early galaxies do pose a problem, or do pose, well, they do pose a problem for our current models. They put a constraint on our models, which right now the models are having difficulty actually explaining. So yeah, I'll get in all that in about 40 minutes. And like I said, after I go through my spiel, which hopefully won't take more than a half hour or so, I will allow people to come on with me, have a conversation. We'll talk about that. If that gets boring, then we can talk about other stuff. So yeah, I'm excited about it, and I'm looking forward to it. All right, unless there are any questions, I will sign off now and hopefully see you all in about 40 minutes. I know for the European folks, you probably need to be going to bed soon, but yeah. So clear skies. Peace out. Nimrod, it starts at 4:30. So right now is 3:51. So 40 minutes.